Give me 20 minutes. Just 20 minutes, and I will make linear regression click forever. You here just fit a line to the data. How hard can that be, right? But then you hit the wall. Suddenly you're drowning in jargon. Loss functions, gradient descent, cost surface. What even is a learning rate? And then someone mentions the normal equation and your brain just shuts down. Let's cut through all of that noise. We'll use a simple problem, student performance. Can we predict an exam score based on hours studied? Look at this data. 1 hour, a score of 2. 2 hours, a score of 4, and so on. When you plot this data, you get these points. The challenge? Fit a single line that best represents all of them. Here is my promise. By the end of this, you will master the 3 pillars and the one incredible shortcut. First, the model, the actual formula. Second, the loss, how we calculate error. Third, the optimizer, gradient descent, the process of getting better. And finally, the shortcut, the normal equation that solves it all instantly. These components are the engine. Now, let's build it, piece by piece. At its heart, linear regression is about summarizing reality. And how do we do that? With one line, to rule them all. Now, if we plot our student data points, we get a little cloud. So let's try to draw a line through them. Here's attempt 1. As you can see, this is a pretty bad fit. It misses the trend completely. It doesn't really tell us anything useful. Okay, let's try again. Attempt 2. Now this line, this is a good fit. Notice how it passes right through the middle of that cloud of points. That's what we're aiming for. This line summarizes the relationship. So here's the secret. Finding the best fit is just searching for the perfect W and the perfect B. Let's build some intuition for that weight W. If you have a really high W, as you see on the right, that means the input is very important. A single hour of studying gives you a huge score boost. But if you have a low W, like on the left, it means the input, well, it doesn't matter that much. 1 hour of study only gives you a tiny boost. But here's the thing, life is complicated. One input is rarely enough to predict something meaningful. So let's look at a new problem, house prices. Here we want to predict the price Y based on 2 things, the size of the house, which we'll call x sub 1, and the number of bedrooms, which we'll call x sub 2. Now, on the left, you see our old model with just one feature. It was a line, y hat equals w times x plus b. But with 2 features, we're now fitting a plane. The equation looks very similar. Y hat equals w sub 1 times x sub 1 plus w sub 2 times x sub 2 plus b. And the logic is the same. W sub 1 is just the price per square foot. W sub 2 is the price per bedroom. And b is the base price of the land. The logic remains identical. We just have more weights to find. Okay, so now we have the model. It's an equation that can make predictions. But here's the crucial question. How do we know if it's wrong? Your eyes can tell which line is better, but your computer is blind. It can't see the data points. It needs a number. That's the loss function. Think of it as a score for how terrible we are. A high score is bad. A low score is good. So what exactly is error? Look at this diagram. The error is just the vertical distance between the real point and our line's prediction for that point. That's it. Now, the industry standard for measuring this badness is called the mean squared error, or MSE. And here's the formula for it. Now, I know this looks a little scary, but it's actually incredibly simple. We just do 3 things. First, the difference. We calculate the error for a single point. That's just y hat minus y, the prediction minus the actual value. Second, we square it. We take that error and multiply it by itself. This does 2 very important things, which we'll get to in a second. And third, the mean. We do this for every point in our data. Add up all those squared errors and then just find the average. That gives us one single number, our final score. But why square the error? Why that specific step? It's for 2 critical reasons. First, no cancellation. Errors shouldn't be able to hide each other. Imagine we have 2 points. For the first one, our error is -5. For the second, our error is +5. If we just added them up, the sum is 0. It looks like a perfect model, but it's terrible. It's just getting lucky. But if we square them first, -5 squared is 25, and +5 squared is also 25. The sum is 50. That is an honest score. It reflects the real amount of error. Second, severe punishment. We hate big mistakes. Squaring the error makes big mistakes seem way worse. An error of 2 becomes 4. Not so bad. But an error of 10 becomes 100. The loss function is basically screaming at the model, don't you dare be far off. Okay, let's make this real. Let's calculate the loss for that first bad guess we had. The model was y hat equals 1x plus 1. So our slope is 1 and our bias is 1. Let's walk through this table. For the first data point, x is 1 and the actual y is 2. Our model predicts 1 times 1 plus 1, which is 2. The error is 2 minus 2, which is 0. And 0 squared is 0. Easy enough. Next point. X is 2, actual y is 4. Our model predicts 3. The error is 3 minus 4, which is -1. Squared, that becomes +1. See the pattern? We just repeat this for all the points. For x equals 3, the error is -1, squared is 1. For x equals 4, the error is +1, squared is 1. And for x equals 5, the error is +1, squared is 1. Now we sum up all those squared errors, and we get a total of 4. To get the final MSE, we just divide by the number of points, which is 5. So 4 divided by 5 gives us an MSE of 0.80. That's our score. Okay, let's do this again, but for our better guess. This time the model is y hat equals 0.6x plus 2.5. The process is exactly the same. We plug in each x, get a prediction, find the error, and square it. For x equals 1, the squared error is 1.21. For x equals 2, it's 0.09. Then 0.49, 0.81, and 0.25. We add all of those up, and the sum of squares is 2.85. Divide that by 5, and our final MSE is 0.57. And there you have it, the verdict. For line 1, that bad guess, the loss was 0.80, a high loss. For line 2, our better guess, the loss was 0.57, a low loss. The math confirms what our eyes knew all along. We now have a reliable way to score any line. So, we found the score. But we can't just sit here guessing forever. How do we find the perfect W and B? We don't guess, we hunt. We have a map, now we need a compass. That compass is called gradient descent. Let's think about this visually. Imagine the loss function, this mean squared error, as a giant hilly landscape. Every possible combination of our weight and bias is a different spot on this landscape. And the altitude, the height at that spot, is the error. Our goal is simple. We want to walk down to the very bottom of the lowest valley. That's the point of minimum error. But here's the challenge. The problem is, we are in a thick fog. We can't see the whole landscape. We have no idea where the bottom is. All we can do from right where we're standing is feel the slope of the ground beneath our feet. So what's the strategy? It's called gradient descent, and it's actually incredibly simple. There are only 3 steps. 1, check the slope. This is what we call the gradient. We're just asking a simple question. Which way is downhill from here? 2, take a step. Move slightly in that downhill direction. And 3, repeat. You just keep doing that, checking the slope, taking a step, checking the slope, taking a step, until you finally reach the bottom. Okay, let's formalize that. The algorithm is a simple update rule. For every single parameter in our model, in this case W and B, The new value is equal to the old value minus some stuff. Let's break that stuff down. It's just two things multiplied together. First is alpha. Alpha is the learning rate. This is just the size of the step you take. And you have to be careful with this. If you take steps that are too big, you might jump right over the bottom of the valley and end up on the other side. But if your steps are too small, it could take you forever to get there. The second part is the gradient. This is the slope. It tells us the direction of the steepest ascent, the steepest way up the hill. That's why we subtract it. We want to go down. So, the big question is, how do we find the gradient? How do we calculate the slopes for our weight W and our bias B? Well, these formulas are derived by taking the derivative of the mean squared error function. We won't do the calculus here, but these are the results. The slope for W is 2 over n times the sum of the error multiplied by the input x. So it's the error weighted by how big the input was. The slope for B is even simpler. It's just 2 over n times the sum of the error. It's basically just the average error. Let's make this real. Let's do a walkthrough with our student exam data. Remember our 5 data points. We have 5 of them, so n equals 5. Step 0, initialization. We have to start somewhere, so let's just pick a random point. How about the worst possible point? W equals 0 and B equals 0. As you can imagine, the fit is terrible. If you calculate the mean squared error loss for this line, it's a whopping 17.2. Okay, let's take our first step. Step 1, calculate the gradients. Our current model is W equals 0, B equals 0, so our prediction, y hat, is always 0. And let's set our learning rate, our alpha, to a small number like 0.01. Now look at this table. For the first row, x is 1, the true y is 2. Our model predicts 0. The error, y hat minus y, is negative 2. And the error times x is also negative 2. We just do this for every single data point. For x equals 2, the error is negative 4. Error times x is negative 8. For x equals 3, error is negative 5. Error times x is negative 15. And so on. At the bottom, we get the sums. The sum of the errors is negative 20. The sum of error times x is negative 66. Now we just plug these into our formulas. The gradient for W is 2 over 5 times negative 66, which equals negative 26.4. The gradient for B is 2 over 5 times negative 20, which is negative 8.0. Those are our slopes. That tells us which way is uphill. Now for step 2, update the parameters. We have our learning rate, 0.01, and we have our gradients. The gradient for W, which we'll call dW, is negative 26.4. And the gradient for B, dB, is negative 8.0. So our new W is the old W, which was 0, minus 0.01 times negative 26.4. A minus and a minus make a plus, so our new W is positive 0.264. Same thing for B. The new B is 0, minus 0.01 times negative 8.0, which gives us positive 0.080. So, what's the result? After just one step, did we improve? We started with W equals 0 and B equals 0, and our MSE loss was a terrible 17.20. After just one step, our new W is 0.264, our new B is 0.08, and our new MSE is 11.45. Yes, we successfully moved down the hill. We made the line better. And the magic is, we just do this again, and again, and again. We are walking to the bottom. If we repeat this loop 1,000 times, look what happens. At step 0, the MSE is 17.2. After one step, it's 11.45. After 10 steps, the MSE is already down to 0.94. By step 100, we're at 0.50. And by the time we hit step 1000, our parameters have settled. W is 0.60, B is 2.20, and the MSE is 0.48. We found it. We found the optimal line. Y equals 0.6x plus 2.2. So, it works. This simple process of checking the slope and taking a tiny step over and over again found the best possible answer. But it took 1,000 steps. That feels a little slow. The question is there a cheat code? What if I told you there's another way? It's time to stop walking and start teleporting. The normal equation is like being in a satellite looking down from space. You see the entire landscape all at once, and you can just point and go directly to the bottom. An instant answer. So what is this one-shot formula, this magic teleportation device? Calculus tells us that the bottom of the valley is where the slope is 0. And if you do the math to solve for that exact point, you get this. This is the normal equation. Now don't worry, it looks a little scary, but it's actually pretty straightforward. Let's break it down. That first symbol, theta, is just a box that holds up parameters. For us, that's our bias B and our weight W. The letter X is our design matrix. This is just our input data, our hours studied. With a little trick, we add an extra column of ones. More on that in a second. The letter Y is our target vector. Simple enough, that's just the actual test scores we're trying to predict. And finally, that little -1 exponent, that means matrix inverse. This is the heavy lifting. This is the core of the calculation. So let's do it! Step 1, build the matrices. Here's our data again on the left. To build matrix X, we take our inputs, 1, 2, 3, 4, 5, and we stick a column of ones right next to them. That column of ones is what allows the formula to solve for the bias term B. It's a neat little linear algebra trick. And for vector Y, that's just the answers. The scores 2, 4, 5, 4, and 5. Easy. Now for steps 2 and 3, the heavy lifting. We need to calculate X transpose X inverse. First, we multiply the transpose of X by X itself. I won't bore you with a step-by-step matrix multiplication, but the result is this little 2x2 matrix here. 5, 15, 15, 55. This is sometimes called the covariance matrix for the stats nerds out there. Then we have to find the inverse of that matrix. Again, it's a standard mathematical procedure, and the result is the matrix you see on the right. 1.1, negative 0.3, negative 0.3, and 0.1. Now, here's a super important warning. Inverting a tiny 2x2 matrix is fast, but inverting large matrices is very slow. The complexity is O of n cubed, which means the time it takes grows exponentially with the number of features you have. Keep that in mind. Okay, we have all the pieces. Let's get the final result. Step 5, we just plug everything into the formula. We take our inverse matrix, X transpose X inverse, and we multiply it by another piece we calculated, X transpose Y. And when we do that one final multiplication, boom, out pops the answer, a vector containing 2.2 and 0.6. We've solved it instantly. The bias B is 2.2. The weight W is 0.6. So for our student performance problem, the result is the equation y equals 0.6x plus 2.2. This isn't an approximation. This is the exact mathematical bottom of the valley, the perfect answer found in one single calculation. No steps, no learning rate, just the answer. So this seems amazing, right? Why would we ever use the slow walking method? Well, there are trade-offs. Let's compare them. Think of gradient descent as the hiker. Its biggest advantage is that it's scalable. It works even with millions of features. And each update step is mathematically cheap. But the downsides are that you have to choose a learning rate, alpha, and it's iterative. It can take many steps. You use the hiker for big data and for all of deep learning. Now think of the normal equation as the teleporter. Its advantages are that it's direct, a one-step solution, and it's easy. There's no alpha to tune. But the downsides are huge. That matrix inverse is heavy. It's slow, O of n cubed, and it takes up a ton of memory. Your computer will literally crash if you try to do this with a huge feature set. So you only use the teleporter for small datasets. Maybe less than 10,000 features is a good rule of thumb. So there we have it. We can find the optimal line by walking down the hill, or by teleporting there instantly. 20 minutes ago, we had nothing but data. And now we have an engine. This diagram shows the entire machine learning loop. Data goes into the model makes a prediction, the loss function scores how wrong we are, and the optimizer updates the parameters to make it better. Round and round. But here's the thing. This is not just math. This is the DNA of machine learning. Your new supervised learning toolkit. The model is the predictor. The loss is the judge. The optimizer is the teacher. And here's the secret. Deep learning is just this, but bigger. You've done it. You've built the foundation. Now, go build the future.